Okay. Hi, everyone. Okay, welcome back. So today we're going to continue to talk about the continuous time Markov chain with several different example problems. And just to let you know, today's example problems are extracted from one of our textbook, Introduction to Probability Models by Sheldon Ross. Okay. Morning. Okay, so here's the first problem. So, could you take one? Okay, the first problem we consider repair shop example. So each time a machine is repaired, it remains up for an exponentially distributed time with rate lambda. And then fails. And its failure is either of two types. If it is a type 1 failure, then the time to repair the machine is exponential with rate mu1. And if it is a type 2 failure, then the repair time is exponential with rate mu2. And each failure is independently of the time it took the machine to fail. A type 1 failure with probability p, and a type 2 failure with probability 1 minus p. Then there are a series of questions we're going to answer for it. What proportion of time is the machine down due to type 1 failure? Thank you. And what proportion of time is it down due to a type 2 failure? And what proportion of time is it up? Okay, so it looks like once you build up our Markov chain model and then determine the steady-state probability distribution, then we can answer all three of these questions right away, right? Okay, so okay, let's build up a continuous time Markov chain model for this example. Okay, so first let's define the state of system. How do you define the state of system? Of course, it's going to be the state of the machine, right? That can be the state of system. So let's say state 0 represents if the machine is up, okay? So machine is working, okay, right? In other words, state 1 means that when the machine is down, okay? So the machine is down. But the down of each machine can due to two different reasons, right? So type 1 failure or type 2 failure. So what I would do is I'm going to have another state, so state 2. And state 2 also represents machine is down. But the state number 1, machine is down due to type 1 failure. Okay? Whereas state number 2 means that the machine is down due to type 2 failure. Okay? Does that make sense? So using this 3 state, we're going to build up the Markov chain model. Okay, so let me give you 1 minute. Why don't you do that? We'll come back. Okay? Make sure. So, did you do it? Okay. So let's draw the transition diagram here. So we're going to have 0. And then let's have 1 down here. And 2 down here. Okay? Is that clear enough? Okay. So according to the problem description here, each time a machine is repaired, it remains for an exponentially distributed time with rate lambda. It then fails. So lambda is the failure rate, right? Becomes the failure rate. And it says it then fails, and its failure is either of 2 types. If it is type 1 failure, the time to repair the machine is exponentially distributed with rate mu1. If it's type 2 failure, then the repair rate would be mu2, right? So here, I draw 1 to 0 would be what? That is the repair rate, which is mu1, right? Likewise, number 2 to 0 would be another repair rate, mu2. Does that make sense, right? Okay, then how could it handle the failure rate? It does say lambda would be the failure rate. So if I break it down to, let's say, lambda 0,1 here and lambda 0,2, right? Then later on, we know that lambda 0,1 and lambda 0,2 would be what? Is that going to be equal to lambda? Is that right? And down there in the problem description, it does say each failure is independently of the time it took the machine to fail. And here, type 1 failure with probability P and type 2 failure with probability 1 minus P. So we need to include this, right? Probability. How? How would you do that? Huh? So here, lambda 0,1 is 1. That's going to be lambda times p. Likewise, here, lambda times 1 minus p. Does that make sense? Okay? So, here, so let's write a balance equation. So for each state I, what you're going to do is, for each state, probably I don't need to write down. Okay. Well, yes. Okay. We're going to write up the maybe left-hand side is transition rate from each state I is equal to transition rate into state I, right? That's the balance equation. So we're going to do this for each state 0, 1, 2. Okay? So let's say state 0. What is that? That's going to be, okay, transition rate from state 0 would be lambda p, right, plus lambda 1 minus p times pi 0, because those two rates are start from state 0, right, is equal to 1. Transition rate into state 0. That's going to be mu1 pi 1 plus mu2 pi 2. Is that correct? Of course, here p plus 1 minus p is 1, right? So actually in this case, the left-hand side is just lambda times pi 0. Is that right? So we have actually left-hand side can be expressed by lambda. Is that right? Okay. What about state 1? That's going to be lambda p, right, pi 0 equals mu1 pi 1. So if you continue on this, for state 2, that's going to be lambda times 1 minus p times pi 0 equals mu2 times pi 2, right? So we have lambda times 1 minus p pi 0 equals mu2 pi 2. Is that correct? And since they are linearly independent, we just need to choose one arbitrarily. So I'm going to take out the first equation. Instead, we're going to have pi 0 plus pi 1 plus pi 2 equals 1. Okay? So we're going to solve these three equations to determine the steady-state probability distribution. Is that correct? So from, okay, let's say this is equation 1, 2, 3. And from 1, we have pi 1 is equal to lambda p over mu 1 pi 0. Is that correct? Right? Likewise, from equation 2. We have pi 2 equals lambda times 1 minus p over mu 2 pi 0. All right? So we can rewrite equation 3 using 1 prime and 2 prime. Okay? So that's going to be pi 0 plus lambda p over mu 1 pi 0 plus lambda times 1 minus p over mu 2 times pi 0 is equal to 1. Is that right? So you should be able to get pi 0 value. So if you take out pi, then pi 0, then it's going to be 1 plus lambda p over mu 1 plus lambda 1 minus p over mu 2 equal to 1. Is that right? So what is pi 0? Pi 0 is 1 plus lambda p over mu 1 plus lambda 1 minus p over mu 2. Like this. Is that right? So let's go back to the problem description here. What is the question? First question is, what proportion of the time is the machine down due to type 1 failure? How'd you answer? Going back to the state definition. State 1 tells you that, right? Machine is down due to type 1 failure. So the answer for the first question is this, right? Once you get pi 0 from this, just plug in there, then you should be able to determine pi 1 value. Is that all right? Then the next question, what proportion of the time is it down due to type 2 failure? Similarly, pi 2, you can get the value of pi 2, right? That's going to be the answer for that. And the third question, what proportion of time is it up? Of course, that's about pi 0, right? Does it make sense, right? Okay, now let's work on the next question, which is part 2. So let me give you a couple of minutes. Why don't you think about how to start this problem? As usual, you need to define the state of system for your Markov chain model, right? And then you can move on from there. Okay, so let's read the problem description together. After being repaired, the machine functions for an exponential time with rate lambda and then fails. Upon failure, a repair process begins. The repair process proceeds sequentially through k distinct phases. First, a phase 1 repair must be performed, and then a phase 2, and so on. The times to complete these phases are independent, with phase I taking an exponential time with rate mu I. And I can take the values from 1 to k. Okay? And we'd like to know what proportion of time the machine undergoing a phase I repair is, and the proportion of time the machine is working. Okay? Okay, so how did you define the state of the system? Let me have the new screen. Oh, okay, just press this. So what if you define the state of system as the number of machines working or number of machines failed? So if I say number of machines failed, so state I represents the number of machines failed. Okay? Then, sorry, it's 0 and 1, something like this. Obviously, the failure rate is lambda, right? Then what about the service, the repair rate? Okay, this problem is quite different from what you've considered earlier, right? So it looks like the major difference is, unlike other cases we handled earlier, in this problem, there are many different steps for a repair process, right? So it looks like it's going to take mu1, mu2, mu3, and so on. And then it looks like there are k different repair process, right? After you've done everything, then the machine will be working. Okay, is that right? So I believe defining the state of system in this way won't work. Okay, quite well. So let's redefine the state of system. So this time, I do say state 0 means the machine is working. Just like that, right? However, we're going to define state I, which represents that you are in, it is in repair phase I, okay? Repair phase I. Of course, I can take the values from 1, 2, 3, and so on, up to k minus 1 and k. Is that right? So how many states we have? In total, there are k plus 1 states. Okay? Are you following me? Right? So using this new state of system definition, we can draw a transition diagram. So let's say we have state 0. In this state, machine is working. And then we have state 1 here. So this is a failure rate, right? Which is lambda. And then let's say we have many different states down here. So we have, this is going to be phase 1 repair process, phase 2, phase 3, and so on. Okay? So we have, let's say this is 1 and subscript, or let's say this is 1 subscript 1, 1 subscript 2, 1 subscript 3, 1 subscript 4, and then here 1 subscript k. Okay? So this is going to be mu1, mu2, mu3, and mu4. This is going to be mu k minus 1. And then finally we have mu k down here. After that, the machine is working. Okay. Does that make sense? Is that right? So let's say this is state 1, and this is state 2, state 3, 4, and then here, k, for the simplicity of the problem. Okay? But you do know that these states from 1 to k is referring to in repair phase. Okay? So based on this, again, let's build up a balance equation. So for state 0, what do we have? It's going to be lambda pi 0 equals 1. Transition rate into state 0 is coming from state k, right? Which is mu k. So it's going to be same as mu k times pi k. Is that right? How about state 1? That's going to be mu1 pi 1 equals lambda pi 0. How about state number 2? Mu2 pi 2 equals mu1 pi 1. So if you keep going, then what about the state number 3? Mu3 pi 3 equals mu2 pi 2. And so on. And then what about state number k? That's going to be mu k times pi k equals mu k minus 1 times pi k minus 1. Is that right? So from this, you know that so see that this left-hand side same as right-hand side, right? Again, this is same as this. This is same as this. All the way. Okay? So what you can draw from this system of linear equation is pi I is equal to what? Lambda over mu I times pi 0. Is that correct? So what I did is, instead of k down here, I used I. Okay? So here, pi I is equal to lambda over mu I times pi 0. Is that right? So, okay, let me rewrite down this. We come up with this lambda over mu I times pi 0. So we come up with this. And we also have sum over pi I equal to 1, right? So use this. Then you should be able to determine pi's. So if you plug in into here, okay, let's see. Let me just write down. Okay. Let's say this is equation 1. So if you use this for equation 1, then 1 can be rewritten down as pi 0 plus what? Lambda times lambda over mu 1 pi 0, lambda over mu 2 pi 0, and so on. Is that right? Because of this. Instead of pi 1, we're going to have lambda over mu 1 times pi 0. Instead of pi 2, we have lambda over mu 2 times pi 0. Like this. Make sense? And then finally, you have lambda over mu k times pi 0 is equal to 1. Okay? So if you take out pi 0, then what's left over? 1 plus lambda over mu 1, lambda over mu 2, up to lambda over mu k equals 1. So what is this? This is same as using summation. You can say sum over I equals 1 to k. Lambda over mu I is equal to 1. So what is pi 0? Pi 0 is 1 plus sum over I equals 1 to k lambda over mu I. Then inverse. Okay? Then how'd you get pi I? Pi I can be obtained from here. So once you get pi 0, you can get pi I, which is lambda over mu I times pi 0. So we already answered for those two questions, right? So how do you answer for part A? What proportion of time is the machine undergoing a phase I repair? This. Right? Second question, what proportion of time is the machine working? This. Is that right? Very easy. So once you build up your Markov chain model, then answering the question would be rather trivial, okay, relatively. Of course, the building up the Markov chain model is the most important thing. To do that, how to define the state of system is a very critical thing to do. So what you need is just practice, practice, practice. Okay? Okay, now let's move on to the next problem set. Okay. So again, let me give you 2 minutes. So please think about how do you start the problem. Okay? Okay, so it's part 3. A single repair person looks after both machines 1 and 2. And each time it is repaired, machine I stays up for an exponential time with rate lambda I. Of course, since we are dealing with only 2 different machines, I can take only 2 different values. They are 1 and 2. Okay? And when machine I fails, it requires an exponentially distributed amount of work with rate mu I to complete its repair. The repair person, excuse me, the repair person will always service machine 1 when it is down. For instance, if machine 1 fails while 2 is being repaired, then the repair person will immediately stop work on machine 2 and start on machine number 1. Then we'd like to know what proportion of time the machine 2 down. Okay. So let's define the state of system. Okay. So how do you define the state of a system? Let's go back. Of course, each state should represent different status of each machine. Okay? So intuitively, I do that. Since there are two different machines, each machine can take two different states, right? Either machines down or machines up. So we're going to have 4 different states, right? That's what I'm going to do. So let's say state 0 represents no machines down. And state 1, let's say machine number 1 is down and machine number 2 is up. Okay? State number 2, reverse. Machine 1 is up and machine 2 is down. And then the last state, state number 3, let's say both machines are down. Okay? So both down. Both machines are down. So using these 4 different states, we are going to build up our Markov chain model. Okay, so are you ready in that? So I'm going to draw 0 here and 1 here, and then let's say 2 down here and 3 down here. Okay? So here both machines are up, right? Down here, both machines down. Here, first machine, machine 1 is down, and machine 2 up. So this is machine 1 and machine 2. Here, first machine is up and second machine is down. Okay? So this is machine 1, machine 2. Okay, so starting from state 0, what transitions occur? So first, the machine number 1 can fail, right? What is that failure rate? Lambda 1, right? So after that, the first machine is down, right? So starting from 1 then, we're going to have repair rate, right? What is this? First machine has been repaired, right? So it's going to be mu1. Is that right? So what other possibilities do we have starting from 0? Second machine can be failed as well, right? So we're going to have failure rate all the way down here. What is that? Lambda 2. So that second machine is down. Then there is a service rate, right? Which is mu2. Is that right? Okay, now starting from state number 3. I'm sorry, state number 1. What transition rate do we have? We already considered this, right? What other possibilities do we have? There is a possibility that the second machine can be down, right? So what is that? It's going to be like this all the way. What is that rate? That's lambda 2, right? Then, do we have this transition rate? Service rate? No, it's not going to happen. Why? Because according to the problem description, if both machines down, then what happened? Repairman will always service machine 1. Okay? If both machines down, right? So this never happened. Okay? So I'm going to delete this because this never happened. Okay, now start from state number 2. Let's see what transitions occur. We already considered this, right? What other possibilities do we have? Here, the machine number 1 can be down, right? What is this? That's going to be lambda 1, right? And then, what about this then? That's going to be mu1, right? That is the repair rate for machine number 1. Okay? So let me write down this. This is mu2. So let me move this. And then this is mu1, right? Does that make sense, right? Okay, now start from state number 3. Let's see what transitions occur. I think we already addressed everything, right? Starting from number 3. Because we addressed this, we knew that from state number 3 to 1 never happened, right? So I believe we've done all the transitions.
1 to 2.
Sorry? 1 to 2? How that can happen?
Machine 1 is down at state 1 and is up in state 2. So
No, that doesn't happen at the same time. Okay? So nothing's going to happen between these two. It's the same. Nothing's going to happen. This. Okay? Okay. Now, based on this, let's construct the balance equation. Okay? So, for state 0, what do we have? Transition rate from state 0 would be lambda 1 plus lambda 2 pi 0. And then transition rate into state 0. That's going to be mu1 from pi 1. And then mu2 from pi 2. Is that right? And for state 1, what do we have? Mu1 plus lambda 2 pi 1 is equal to lambda 1 times pi 0. Is that right? So we just need to keep going. State 2, mu2 plus lambda 1 pi 2 equals lambda 2 pi 0 plus mu1 pi 3. Is that right? And for state number 3, what do we have? That's going to be mu1 pi 3 equals lambda 2 pi 1 plus lambda 1 pi 2, right? So we're going to take out one of these linear equation, arbitrarily choose one, then add pi 0, pi 1, pi 2, pi 3's, so equal to 1, right? So you're going to solve this system of linear equation to determine steady-state probability distributions. Okay, so now go back to the question. What is that? We want to know proportion. Oh, okay, what happened? Okay, we want to know the proportion of time the machine to down. Okay? So, how do you answer that? Machine 2 is down. How do you go back to see how we define the state of system? So if you look at this, state number 0, machine 2 is up, right? Here, machine 2 is up. How about this? State number 2, machine 2 is down. State number 3, machine 2 is down. So if you are in state number 2 and 3, the machine 2 is down. So how do you answer? How do you answer? Yeah, just add up. Pi 2 plus pi 3 will be the answer, right? But in the exam, I want you to provide me the exact value, okay? Instead of just writing down this, okay? Okay, now let's move on to the last question for today. Okay, so in this example, a job shop consists of 3 machines and 2 repairmen. And the amount of time a machine works before breaking down is exponentially distributed with mean time of 10. If the amount of time it takes a single repairman to fix a machine is exponentially distributed with mean 8, then what is the average number of machines not in use, and what is the what proportion of time are both repairmen busy? Okay, so highly likely, once we build up the Markov chain model and determine the steady state probability distribution, then we should be able to answer for these 2 questions very easily. Okay, so let's do that. Okay. So let's define the state of system. Let's say state I represents the, okay, this time the number of machines broken down. Okay. So that's going to be our state of system, number of machines broken down. And then, okay, this repair shop has 3 machines. Okay, and then 2 repairmen. So we may think like this way: this Markov chain model consists of 3 customers and then 2 servers. Okay, does that make sense? So let's build up our Markov chain model. So we have 0, 1, 2, and then 3. Okay, because we are dealing with only 3 machines, so we don't have 4, right? Because at most 3 machines can be broken down. Okay, so write down here. Since we are dealing with 3 machines here, all 3 of them working okay, is in good condition. Now, this state, only one of them has been broken down, right? Here, 1 is okay. We have 2 broken down. And then here, all 3 of them doesn't work, okay? Now, we need to specify failure rate here. So what is that? It does say, okay, it does provide you the failure time, mean failure time is 10. So what is the failure rate then? 1 over 10, right? 1 over 10 is the failure rate. That is failure rate. Then what is the repair rate? Repair time is given as 8. So repair rate would be 1 over 8. Is that right? So those are the unit value. So here we have 1 over 10. That is the failure rate for each machine. But in state number 3, how many machines are in good condition? 3. which means you need to multiply by 3. Right? Because all of these 3 machines have the same failure rate of 1/10. Okay. So with this in mind, you can do this. What is the failure rate at this time? Multiply by 2, because there are 2 good machines, right? Here, it's going to be 1/10. Since there is only one good machine in state number 2. Okay, now starting from 1, state number 1, what is the repair rate then? We notice that repair rate is 1/8, right? So it's going to be 1/8. How about this? Is that going to be 1/8? Multiply by 2. Why? Okay, because in state number 2, 2 machines are down. And then since this repair shop has 2 repairmen, both of them will be busy to take care of these broken down machines, right? Since both repairmen will be busy, you have to multiply by 2. Okay? Similarly, the repair rate would be 1/8 times, what? Is that times 3? If we have 3 repairmen in the system, then you're going to multiply by 3. But the thing is, this repair shop has only 2 repairmen. So even though there are 3 machines broken down, since you have only 2 repairmen, you're going to multiply by 2. Okay? Which means one of the broken machine is on standby. Okay? Make sense? Okay, so since we have completed the transition diagram, and looks like this is one of the burst decimal, right? The number of machines broken down has increased by 1 always, and decreased by 1. And machine failure and service are independent. So this is the burst test process. So we're going to use the streamlined version of balance equation, which is 1 plus 3/10 over 1/8 plus product of the first 2 arrival rate, which is 3/10 times 2/10 over 1/8 times 2/8, right? And then third one, product of the first 3 arrival rate. So 3/10, 2/10, 1/10 over product of the first 3 service rate, 1/8, 2/8, and 2/8. So what is this? That's going to be 1 plus 5, 4, right? So that's going to be 12 over 5, right? The same way, 5, 5, 4, 4. And then this is going to be even 2, 1. So that's going to be 48 over 25. Am I right? Let me know if you find a mistake, an error. Likewise, 5, 5, 5, 4, 4, 4. So 4, 5, 5, 5. And then this is even 2, 1, 2, 1. Okay? So we have what do we have here? 125 and is it 96? Is that right? So what is this? $125. What is this? What is 25 times 12? That's 300. Okay. Plus 5 times 48. 240. Thank you. And then 96. So what do you have here? How much is that? 125, 761? Is that right? Okay. So what is pi 0? 125 over 761. Is that right? And what is pi 1? Pi 1 is 12 over 5 times pi 0. Pi 1 is 48 over 25 pi 0. Pi 2, 96 over 125 pi 0. So you should be able to get all of these values. Okay? Okay, so how do you answer for the first question? It's been asking you the average number of machines not in use. Average number of machines not in use. So if you are in state 0, how many machines are not in use? 0. If you are in state 1, you have 1. State 2, you have 2. State 3, you have 3. Right? So what you're going to do? 0 times pi 0, 1 times pi 1, 2 times pi 2, 3 times pi 3. That's what you need to do. Right? Easy? How about B then? What proportion of time are both repairmen busy? It's also very easy. If you are in state number 0, how many repairmen are busy? No one. How about 1? Only 1 repairman will be busy. How about 2? Both of them will be busy. 3, both of them will be busy. So how do you answer? Pi 2 plus pi 3, right? So once you get each pi values, these are piece of cake, right? Any questions? Okay. Okay, so these are all for today. So next week is your time. Okay. So I'm also very excited to see your presentation. And let me know if you have questions while you are preparing for the project. written report and the presentation as well. Okay? Thank you. Bye-bye.